Hello class. In this video, we are going to talk about how to formulate an LP model for case 2.1. In case 2.1, we have one company called Blue Ridge. Blue Ridge wants to produce two different types of products. One is called Aqua Spa. We can simplify as Aqua. And the other one is called Hydro Lux. We can also call it Hydro. Blue Ridge has 200 pumps in total for the next production cycle. And for each Aqua, it requires 9 hours of the labor and 12 feet of the tubing. For each Hydro, we need 6 hours of the labor and 16 feet of the tubing. In total, Blue Ridge expected to have 1,566 production labor hours and 2,880 feet of the tubing. As estimated based on the historical data, Blue Ridge have a margin profit of $350 for Aqua Spa and $300 for the Hydro Lux. One of the key questions for us is how to figure out what is the optimal solution. Although this problem does not look very complex, but actually it's not easy to figure out what is the optimal solution without going through a formal procedure of linear programming. So next, we try to figure out how to write down the LP model. In order to write down the LP model, it is very useful for us to have the relation table. As shown below, in the relation table, we have Aqua Spa and Hydro Lux. At the same time, we have the information about the pumps, labors, and tubing. The pumps, labor, and tubing, we call them as resources for the company. So the relation table actually showing the relationship between the product and the resources the company have. In this case, we know that for every unit of Aqua, we have $350 of the marginal profit for Blue Ridge, and we have $300 marginal profit for Hydro. For the resources pump, we have 200 pumps in total. For each pump, we have 1 unit for Aqua, and Hydro needs 1 unit as well. For the labor, we have 9 hours for each unit of the Aqua, and we have 6 hours for each unit of Hydro. In total, we have 1,566 available labor hours. For the tubing, each Aqua needs 12 feet, each Hydro needs 16 feet, and we have 2,880 in total. Actually, this relation table is very useful. We can write down the LP model directly based on this relation table. Although it's not always true for all LP models, but for this case 2.1, we can do so. For example, as we know that we are going to maximize the profit for Blue Ridge. In order to write down the LP model, we can start with the relation table. In the following table, we have the relationship between the product Aqua Spa, Hydro Lux, and those 3 available resources, pumps, labor, and tubing. This relation table is very useful because it shows us the relationship between resources and product, and actually, we can write down the LP model directly based on the information. This relation table is very useful. Actually, we can write down the LP model directly based on this table. For example, for this case, we can write down the objective function directly based on that, and we can have maximize profit, and that will be equal to 350 times the quantity of Aqua Spa. We can temporarily name the notation as A plus 300 times H. And that's the total profit for the Blue Ridge. The objective function of Blue Ridge is subject to the following constraints. So we can put subject to 1 times A plus 1 times H. And that total pump will be used for aqua and hydro. We know that we don't have more than 200 pumps. So in total, all the units of the pump used should be less or equal 200. The same logic applies to labors. We have 9 hours of labor each. So we are going to times A plus 6 times H will be less or equal 1,566. For the tubing, we have 12A plus 16H will be less or equal 2,880. I'm going to show you the procedure step by steps in the next slides. In the first steps, we know that we need to understand the problem. And in this case, we know Blue Ridge is to optimize the profit for 2 types of the product. So we can write down the decision variables, the notations for the 2 products. In this case, we can also use X1 for the number of aqua spots and X2 for the quantity of hydroluxes. As you can see that I use different type of notation just in these 2 slides. In the previous slides, I used A and H. Here I use X1, X2. Actually, it's really up to you to choose what type of notation you use for the decision variables. For this class, typically we don't have many decision variables. So actually it's fine for you to name any decision variables in the way you like. But when you have many decision variables, I would suggest you use X1, X2, X3, X4, X5, so that you can just use number to name after the X. You can even go to 1,000 or 10,000. But if you use different name, like A, H, K, like that could be very confusing for you. Now, after we have decision variables, we can write down the objective function. As we know that we have the marginal profit of 350 for each unit of X1 aqua and 300 for each unit of hydro. So our objective is to maximize 350 times X1 plus 300 times X2. The fourth step is try to state all the constraints we have. In the previous relation table, as we show over here, we know that we want to show the relationship between the number of the requirements of the pumps for each product. So in this case, we can write down 1x1 plus 1x2 will be less or equal to 200 pumps. For the labor, we have 9x1 plus 6x2 less or equal 1,066. And for the tubing, we have 12x1 plus 16x2 less or equal 2,880. Finally, we are going to specify any upper or lower bounds for the decision variables. In this case, we know that we cannot produce negative number of the aqua or hydro, so we need to keep those quantities as non-negative. So we have x1 larger or equal 0, x2 larger or equal 0. So after we finish all these steps, we can sum them up as this LP model. In this LP model, we are going to maximize the total profit for the company as 350 x1 plus 300 x2, subject to the following constraints: the pumps, the labor, and the tubing, and those 2 non-negative constraints. Thank you.